Hi, and welcome to this short tutorial on sketching the magnitude and phase Bode plots of frequency responses. So in this tutorial, I'm going to work out some examples on how to sketch these two plots for LTI systems. Okay, I'm going to consider problems of increasing complexity as you move forward in the video. So if a particular problem seems very trivial to you, please feel free to skip it and move on to the next one. Okay, so let me minimize this video over here and let's get started with the tutorial.
The basic idea underlying Bode plots is to first express the transfer function h of s as a product of building blocks. So the building blocks that we consider over here are listed in this slide. So you've got these four different building blocks over here, and the idea is to express a rational transfer function h of s as a product of these building blocks, right? Now let's take a look at an example and understand how to express such a function as a product of building blocks. So in this question, we are asked to compute the transfer function first. H of s is minus 1 over 2s, right? And then based on this transfer function, we got to factor it as a product of building blocks, right? So clearly there is a 1 over s factor in h of s, right? So I can write h of s as minus 1 half times 1 over s, where the first building block is a constant, right? Where k is minus half, right? And the second building block is 1 over s, right? So I can say that h of s equals h1 of s times h2 of s, where h1 of s equals minus half and h2 of s equals 1 over s, right? Now, the next step is to sketch the Bode plots associated with each of these, that is the Bode plot for h1 of j omega, Bode plot for h2 of j omega, and then to get the Bode plot of h of j omega, we are just going to sum up the two plots that we get over here, right? So let's take a look at the Bode plot for h1 of j omega. h1 of j omega, as we just saw in the last slide, is minus half, right? Now, what about the magnitude sketch for this h1 of j omega? Okay, so in Bode plot, recall that the frequency is taken on a log scale, right? Which means we got points like 0.1 and 1 and then 10, 100, etc., right? Next, we need to calculate 20 log to the base 10 of absolute value of h1 of j omega on the vertical axis. And what is 20 log to the base 10 of absolute value of minus half? So that is going to be 20 log to the base 10 of 1 over half, and that is equal to 20 log to the base 10 of 2 to the minus 1, okay? And you can show that it's going to be minus 6 decibels, approximately minus 6 decibels, right? So what you have for the magnitude sketch of absolute at h1 of j omega is a flat line at minus 6 dB. What this means is that h1 of j omega results in a constant gain of minus 6 decibels at each and every frequency, all right? Now let's take a look at the second building block, which was just 1 over j omega, right? Because h2 of s is 1 over s, all right? Now we got to sketch 20 log to the base 10 of the magnitude of h2 of j omega, right? And the magnitude of h2 of j omega is the magnitude of 1 over j omega in this example, right? And what is the magnitude of 1 over j omega? You can write that as the magnitude of the numerator, which is 1, divided by the magnitude of the denominator, right? And the magnitude of the denominator in this case is magnitude of j times magnitude of omega. And as you know, because the magnitude of j is 1, you end up with 20 log to the base 10 of 1 over magnitude of omega, all right? Now, in Bode sketches, we just consider the positive frequencies, right? So I can write magnitude of omega as just omega, right? And 1 over omega is omega to the minus 1, okay? And there's a property of logarithms that log of a to the power of m is m times log a, right? So I can push this minus 1 over here, okay? So what I get for the magnitude sketch of 20 log to the base 10 of the magnitude of h2 of omega is a straight line that decreases with a slope of minus 20 decibels per decade. All right. Now let's take a look at the value at omega equals 1 radian per second. So by the way, the x-axis is in radians per second, right? So when omega is 1, minus 20 log 1 is 0, right? So you got 0 decibels over here. Okay. Now when omega is 0.1, okay, so this coordinate over here is going to take a value of plus 20 decibels, right? And at omega equals 10, you're going to have minus 20 decibels. All right. Now, you know that h of j omega is the product of h1 and h2. Okay. So I can apply log on both sides, and what I can say is that 20 log to the base 10 of h of j omega is equal to 20 log to the base, there's a magnitude here, h1 of j omega plus 20 log to the base 10 of the magnitude of h2 of j omega, right? Which means the final Bode sketch for the frequency response of interest h of j omega is going to be the sum of these two sketches that I have over here, right? Now, the sum of these two sketches is very straightforward to figure out, right? Because one of these sketches is just a flat line, and if you add a flat line to another line with a slope of minus 20 decibel per decade, only the intercept changes and the slope remains the same, right? So what I'm going to do now is I'd say, well, I can replace this by h of j omega, and all I need to do is just add minus 6 decibels to each of these points, right? So this point over here would be minus 26 decibels, okay? And of course, this would go up by 20 decibels, because if I move to the left, right, this point would correspond to minus 26 decibels plus 20 decibels, right, which is minus 6 decibels. And I add another 20 decibels over here. So the gain at frequency 0.1 radians per second is going to be 14 decibels. All right. So this is the final Bode magnitude sketch for the frequency response that we had in this example. All right. Now let's take a look at the phase sketch. Now the procedure remains the same. So first we've decomposed h of j omega as a product of h1 of j omega and h2 of j omega. All right. Now we got to figure out the phase of each of these functions over here with frequency, right? So let me mark those points again: 0 0.1, 1, 10, and you could also have 100, etc. Right? So let's first sketch the phase of h1 of j omega. Now, what is the phase of negative half? So if I sketch negative half in the complex plane, it falls over here, right? And the phase of this complex number is 180 degrees or minus 180 degrees, whichever way you look at it. Both are equivalent. So whether you say it's minus 180 degrees or plus 180 degrees, doesn't matter. Okay. So the phase is independent of frequency, and it takes a constant value of minus pi for all omega, right? Now let's take a look at the phase of h2 of j omega. All right. Now, where does h2 of j omega fall on the complex plane? So I'm again going to sketch real and imaginary axis over here, right? And let me take some examples. Let's say omega is 0.1. So what is 1 over j times 0.1? It is 10 over j, which is minus 10j, right? So minus 10j is somewhere over here. All right. And for any positive omega, you can show that 1 over j omega is always going to lie on the negative portion of the imaginary axis, right? So which means the phase of 1 over j omega is going to be minus 90 degrees, right? So I'm going to have a straight line that is flat at minus 90 degrees, right? Now, as you know, h of j omega, the frequency response, is the product of h1 and h2, which means the phase of h of j omega is the phase of h1 of j omega plus the phase of h2 of j omega, right? So all I need to do now is to add up these two sketches over here and then figure out what the equivalent graph is, right? So when I add the two, okay, so let me sketch phase of h of j omega directly. So I'm going to add minus pi with minus pi over 2, and what you end up with is minus 3 pi over 2, and this phase stays flat for all frequencies, right? So this is how you can figure out the Bode phase sketch, by simply adding the phase sketches associated with each building block, right? So as you can see, this is the solution that we had obtained in the last slide. All right, now let's work out another example. We are given a frequency response 1 over 2 plus j omega. The transfer function associated with this frequency response is 1 over 2 plus s. Okay. Now, when you look at this equation, you'd realize that, well, the transfer function over here has a pole at s equals minus 2, right? Because the denominator is equal to 0 when s equals minus 2, right? So you fall into this block over here, right? Now the question is, can we express h of s in terms of this building block, where we have term of the form 1 over 1 plus s times something, right? Where this tau over here needs to be positive, right? Now, can we express this as 1 over 1 plus s times something? So let's take a look. So first of all, from this building block over here, you would see that the constant term in this first order factor is just 1, right? However, we have a 2 over here, right? Now, how do we solve this problem? Well, I can just factor the 2 out in the denominator, right? And what I'd get is h of s equals 1 over 2 times 1 plus s over 2, right? So this is equal to 1 half times 1 over 1 plus s over 2, right? Now, this h of s over here is a product of two building blocks. The first building block is a constant at 1 half, and the second building block, h2 of s, takes the structure of this term, right? Where we have 1 over 1 plus s times something, where the tau is 1 over 2, right? Now, let's make use of this product and figure out the Bode sketches for each of these terms and then add them up. So let's first sketch the Bode magnitude plot, 20 log to the base 10 of magnitude of h1 of j omega as a function of omega, right? Okay. And next we are going to sketch 20 log to the base 10 of magnitude of h2 of j omega as a function of omega, right? So if you recall, h1 of j omega in this example is 1/2 and h2 of j omega is 1 over s plus, sorry, I think it was 1 over 1 plus s over 2. Yeah. So which means you have 1 plus j omega over 2, right? So what is 20 log to the base 10 of 1/2? It's going to be minus 6 decibels. So you're going to have a flat line at minus 6 decibels, right? Now let's take a look at the second term over here, which is interesting, right? So 20 log to the base 10 of the magnitude of 1 over 1 plus j omega over 2, right? Okay. Now for very low frequencies, when omega is negligibly small, right, the magnitude of 1 plus j omega over 2 is determined by the magnitude of this term, that is 1, right, which is 1. Okay, so you would get 0 decibels for very low frequency, right? And the break frequency in this case is exactly the point where omega equals 1 over tau, right, as we've seen in the lecture. So 1 over tau in this case means you have 1 over 1/2, which is 2, right? So the break frequency is 2, right? And for large omega, you can ignore this 1 over here, right? And what you get is 20 log to the base 10 of 1 over omega over 2, right? Which means this function over here decreases with a slope of minus 20 decibels per decade, right? So what I'm going to do now is I'm just going to sketch a straight line that goes down at minus 20 decibels per decade, right? This is something that we've seen in the class, and it's also easy to verify because for a large omega, I can ignore the 1 over here, and all I get is 20 log 10 of 1 over magnitude of j omega over 2, which is same as the magnitude of omega over 2, which is 2 over omega, right? Now, this is equal to 20 log to the base 10 of 2. We're not interested very much in the constant, rather we are interested in the slope, right? Right? Minus 20 log to the base 10 of omega. Okay. This is why, due to the second term, when omega goes up by a decade, the Bode magnitude sketch goes down by a factor of 20 decibels, right? So if I start from omega equals 2 and I jump to omega equals 20, which is 1 decade, right? So the magnitude sketch over here would drop by 20 decibels, right? So this value would be minus 20 dB. Okay. Similarly, if I jump all the way till 200 radians per second, okay, the value here would be minus 40 decibels. All right. Now, you know that the Bode magnitude sketch for h of j omega is the sum of Bode magnitude sketches that we have over here, right? So what happens if I add a minus 6 dB flat line to this curve over here? Well, the slope remains the same, okay? And all I need to do is to just change the values along the y-axis, right? So that is just offset them by minus 6 dB, right? So the magnitude response is minus 6 dB at low frequencies, and as soon as we hit 2 radians per second, it starts to decrease at 20 decibels per decade, right? Now, let's work out the phase sketch next. So h1 of j omega in this example is 1/2 and h2 of j omega equals 1 over 1 plus j omega over 2, right? Now the phase of h1 of j omega is 0 for all omega, right? Because the phase of 1/2 is simply 0. Why? Because 1/2 is a positive real number, right? And let's take a look at the phase sketch for h2 of j omega. So I have the break frequency at 2. All right. Now at omega equals 2, what is h2 of j omega? At omega equals 2, h2 of j omega is 1 over 1 plus j, right? And what is the phase of 1 plus j? It is 45 degrees, right? Pi over 4. And what is the phase of 1 over that? It should be minus 45 degrees, right? So the phase of h2 of j omega is minus pi over 4 at omega equals 2, okay? So just take a note of this, and now let's try to work with asymptotic analysis for a Bode phase sketch, right? So as I mentioned to you, for Bode phase sketch, we need to look at low frequencies as well as high frequency. Now what is low? We take 1/10 of the break frequency, and call it as a low frequency for the sketch, right? So the 1/10 is 0.2, and when the frequency is really low, you can basically ignore this j omega over 2 term, because this is going to be negligibly small compared to 1, right? And what you end up with at low frequency is just 1, and the phase of 1 is 0, right? So it's 0 radians, all right? Now what happens at high frequency? So when omega is large, for large omega, h2 of j omega is approximately equal to 1 over j omega over 2, right? Because I can ignore the 1 over here, right? And the phase of h2 of j omega under such a case is going to be minus pi over 2, right? For large omega, okay? So I'm going to have minus pi over 2 over here, okay? And how do we connect these two? Well, just draw a straight line. Okay. Well, it doesn't look like a good straight line, but yeah, in the exam you could just bring a ruler and sketch a straight line, right? And at 2 over here, you know that the phase should take a value of minus pi over 4. All right, so this is a Bode phase sketch. So let's now work through the final exercise in this tutorial. So as usual, we got to express this transfer function as a product of building blocks, right? So just by looking at this expression, you realize that, well, the transfer function over here has a 0 at s equals minus 1. And as we derived in today's lecture, it's going to have two poles. One pole is at 10 e to the j3 pi over 4, and the other pole is at 10 e to the minus j3 pi over 4, right? So we obtain these poles by simply setting the denominator equal to 0, right? Now, when you got 1, 0, and it's a real valued 0 at s equals minus 1, right? So the block that you need to use is this one, right? And if you got two complex conjugate poles, right, the block that you need to use is this one listed here, right? So let's try to express s plus 1 as 1 plus s times something, right? And this is straightforward. So s plus 1 is the same as 1 plus s times 1, right? And now we got to express this term over here as 1 plus a linear term in s plus a quadratic in s, right? So how do we do that? So as you can see in this quadratic over here, the constant term is 200, while in this building block, the constant term is just 1, right? So how do we get 1 out of 200? So we just simply factor the 200 out, right? And what we end up with is s square over 100 plus square root 2s over 10 plus 1, all right? Okay, so I can rewrite the same thing as 1 plus s times 1 divided by 200 times 1 plus square root 2s over 10 plus s square upon 100, right? So this term over here corresponds to the first block. So let's write that as h1 of s equals 1 plus s times 1. All right. And notice that there's also a constant of 1 over 200 here, right? So h2 of s is simply a constant, which is 1 over 200. And h3 of s is the third standard building block, which is 1 over 1 plus square root 2s over 10 plus s square upon 100. Okay. Now, what is tau associated with the first block? So let me write that in a different color here. So this corresponds to tau equals 1, right? And for the constant, there's nothing to do. K equals 1 over 200, right? And for the third block over here, you would realize that by comparing the quadratic in the denominator with the quadratic we have over here, you could just equate 1 over omega n square to 1 over 100, right? So I'm just equating the coefficient that sits in front of s square, okay? Which means you would end up with omega n, which is the natural frequency, equals 10, all right? And we've also got to figure out the damping ratio, right? So if I just equate the term in front of s over here and over here, you realize that 2 xi over omega n needs to be equal to square root of 2 upon 10, all right? And as we know, omega n is 10 in this example, right? So I can just cancel these two out, and I end up with xi equals 1 over square root 2, which means the damping ratio is 1 over square root 2 for the third block. Okay, so this is how I can figure out the parameters associated with each building block for this particular example, right? Now, the next thing to do for the Bode plot is to first sketch the magnitudes of each of these in the decibel scale, and then add them up to get the final magnitude sketch for h of j omega. So let's get started by first sketching the magnitude of h1 of j omega, which is 1 plus j omega, right? And how is this going to look like? So the idea remains the same. We are going to plot omega in the log scale. So let me mark these points 0.1, 1. Okay, 1 is the break frequency, by the way, because tau is 1. The break frequency is 1 over tau, which is 1 in this case, right? 1 radian per second. Okay, and then I've got 10, and let's also mark 100. Okay, so these points differ by a factor of 10 when I move every unit, right? Now I got to sketch 20 log to the base 10 of magnitude of h1 of j omega. right? Now, once again, the argument goes as follows. Just observe the magnitude for low frequencies and high frequencies, right? So what is low? A low frequency is something that is much less than the break frequency, right? So if the break frequency is 1, so low frequencies would correspond to this regime over here, where if omega is low, I can ignore this term, and the magnitude of h1 of j omega is just 1, right? Which means in the decibel scale, it's a straight line at 0 decibels, right? Now, at 1, there's going to be a transition, right? And to examine this transition, we got to check the magnitude of h1 of j omega for large omega. Okay. Now for large omega, this complex number 1 plus j omega is almost equal to j omega, right? So if this is 1, this is j omega, where omega is large. Okay, if I add a small real value to j times omega, the result is almost the same as j times omega, right? I can just ignore the 1, all right? Now, the magnitude of this thing over here is approximately equal to the magnitude of j omega, which is omega, right? So 20 log 10 of omega represents a straight line over here that goes up at 20 decibels per decade, right? So when omega is 10, you would be having 20 decibels, and when omega is 100, you would be having 40 decibels over here in the Bode sketch, all right? Now, we've got to sketch the magnitude for the second building block, that is h2 of j omega equals 1 over 200, right? So first, what is 20 log to the base 10 of 1 over 200? I can write this as 20 log to the base 10 of 1 over 2, which is minus 6 dB as we already computed, plus 20 log to the base 10 of 1 over 100, which is 10 to the minus 2, and this would give me minus 40 dB, and overall it's minus 46 dB, right? Okay, so I can sketch 20 log to the base 10 of magnitude of h2 of j omega on this plot itself, and it's going to be a straight line at minus 46 decibels, right? And this blue line represents 20 log to the base 10 of mod h2 of j omega, all right? Now we got to compute 20 log to the base 10 of h3 of j omega now, right? So before we do that, let me just write down the expression for h3. h3 of j omega is 1 over 1 plus square root 2 over 10 j omega plus j omega whole square upon 100. All right. Now let's try to sketch this. 20 log to the base 10 of magnitude of h3 of j omega. Right. And I'm going to have these same points that I mark here, 1, 10, 100. Okay. Now note that the natural frequency of this system is 10 radians per second, as we've seen earlier, right? Okay. Now low frequencies are those frequencies over here that are much lower than the natural frequency. Okay. So in this case, what I'm going to do is I'm going to examine what happens to h3 of j omega when omega is very small, right? So when omega is very small, you can basically ignore these terms over here, and h3 of j omega is approximately equal to 1, right? Okay. So what is the magnitude of h3 of j omega? It's 1. So 20 log to the base 10 of 1 is 0, right? So this Bode sketch over here is going to stay at 0 decibels all the way until we reach the natural frequency, that is 10 radians per second, right? Now, when omega is extremely large, so we are looking at the asymptotic case. When omega is large, you can ignore the first order term over here, okay, because we've got a second order term, right? And you can also ignore the 1 for large omega, right? And what is this equal to? It's equal to minus omega square, right? And what is 20 log to the base 10 of 1 over minus omega square with the mod over there? So this is equal to, this thing over here should be equal to 20 log to the base 10 of 1 over omega square, right? And this is equal to minus 40 log to the base 10 of omega, right? So this represents a straight line that goes down with a slope of minus 40 decibels per decade, okay? Okay. So what is the value at 100? It should be minus 40 decibels, right? Because at 10, it's 0 decibels. If I go up by a decade, the magnitude should go down by 40 decibels, right? Now, we've got the sketch for h1 of j omega, the Bode sketch. It's the red line shown there. We've got the sketch for h2 of j omega, the magnitude Bode sketch. It's the blue line. And we've also got the Bode sketch for h3 of j omega, which is the green line, right? So all I need to do now is to just sum up these three sketches, right? Because h of j omega is h1 times h2 times h3, right? And as you know, the magnitude Bode sketch for h is the sum of the sketches for h1, h2, h3, right? So you could take this as an exercise, just sum up the red curve, blue curve, and the green curve, right? And you can clearly see that, well, until I hit 1 over here, the magnitude sketch is 0 plus minus 46 plus 0, which is going to be flat at minus 46, right? At 1, you have this red line increasing with a slope of 20 decibels per decade, while the others remain the same, right? So the sum would also increase by 20 decibels per decade, right? And once you hit 10 and you cross it, you notice that the red line increases at 20 dB per decade, while the green line decreases at 40 dB per decade. So the sum of the three over here would go down at 20 decibels per decade, right? So let me summarize all of them in one single sketch and plot it out. So this is omega. I've got 0 0.1, 1, 10, 100. And we know that this is 20 log to the base 10 of mod h of j omega, right? So this should be flat at minus 46 decibels, right, until you hit 1 radian per second. And from there onwards, it increases with a slope of 20 decibels per decade, okay? And you reach minus 26 decibels, right? And at 10, we realize that, well, it needs to go down at the rate of 20 dB per decade, minus 20 dB per decade. So this is plus 20 dB per decade, okay? And at 100, you would hit minus 46 dB. And at 1000 radian per second, you would hit minus 66 dB, all right? So this is the Bode magnitude sketch for h of j omega. Now let's take a look at the phase sketch now. So for the phase sketch, you once again need to look at the components or the building blocks. So h1 of j omega is 1 plus j omega in this example. h2 of j omega is 1 over 200, right? h3 of j omega is 1 over 1 plus square root 2 over 10 j omega plus j omega whole square upon 100, right? So the phase of h2 is very trivial to compute, right? So phase of h2 of j omega is just 0. So this doesn't contribute at all to the phase plot, because if I add 0, I get the same thing, right? So we just need to sketch the phase of h1 of j omega and the sketch of h3 of j omega and then sum it up, right? So let's take a look at the phase of h1 of j omega, which is the phase of 1 plus j omega, right? Okay. So once again, I've got 0 0.1, 1, 10, 100. Okay. Now, the break frequency over here is 1 radian per second, right? So for low frequencies, which are much lower than the break frequency, right, the term over here, 1 plus j omega, can be approximated as 1, and that needs to have a 0 phase, right? Okay. Now at high frequencies, j omega becomes significant enough. And what is the phase of j omega? Because at high frequencies, you can ignore this one, right? So the phase of j omega is 90 degrees, right? So let me sketch this over here at 0 degrees. And at high frequencies, you know that the phase needs to be 90 degrees or pi over 2, right? Okay. And what happens at 1 radian per second? You end up with the phase of 1 plus j, and the phase of 1 plus j is 45 degrees, right? So this point over here would map to pi over 4. Okay. Now I just need to draw a straight line that connects the 0 and pi over 2, and it needs to pass through pi over 4. All right. So that straight line would look like that. Okay. So this is a phase sketch for h1 of j omega. Now let's figure out the phase sketch for h2 of j omega. Okay. Sorry, it's h3 of j omega, right? Because h2 of j omega was just a constant and it had a phase of 0. All right. Now h3 of j omega is 1 over 1 plus square root 2 j omega over 10 plus j omega whole square upon 100. Okay. So let me sketch over the same scale. All right. Now we got to examine what happens to this denominator over here for low frequencies and high frequencies. Okay. So what is low? A low frequency is something that is much lower than the resonant frequency in this case, which is 10, right? So 10 radians per second, right? So the resonant frequency is 10 radian per second, which is here. And let's say that 1/10 of the resonant frequency is considered low, right? So for low frequencies, you can ignore the terms that are dependent on omega, and h3 of j omega is simply 1, and the phase of that is going to be 0, right? So you're going to have, say, 0 radians phase until you hit 1. And what happens at high frequencies? So when omega is really high, the only term that is significant is the second order term over here, which is omega square, right? Because if I square something, I end up with a large value, right? Okay. What is j omega the whole square? It is negative omega square, right? And I can push this 100 to the top, right? And what is the phase of minus 100 over omega square? It's 180 degrees, right? So you could also write that as minus 180 degrees, right? So when I'm at 100 or beyond, right? So when I'm at high frequencies, which is 10 times the natural frequency and beyond, the phase is going to be minus pi, okay? And after that, I'm just going to draw a straight line, right? And I get that, all right? Now, the phase sketch for h of j omega should be the sum of these two phase sketches. So I go through these two sketches point by point and then just sum them up, all right? So I'm going to leave this as an exercise to you to sum up these straight lines, right? It should be a very trivial exercise. So take that as an exercise and good luck.